So I see Common Lisp, one of the big strengths of Common Lisp, aside from all the technical strengths and everything else that we've talked about, is that it can be a real safe haven for independent developers. And by that I mean it's not controlled by any big company or any big entity like Java is controlled by Oracle. Who knows what they're going to do? .NET, I mean, what's that? So Common Lisp is a platform on the same level as a Java or a .NET. I mean, it is a whole platform. It's not just a language, it's a runtime platform. For managed, it's a platform-based language, which are all the vogue these days. You say, ooh, we got to use a platform-based language like Java, .NET. So, this is what we have, and it's free. It's I don't think I get into any more detail on that. So it has a free and open spec. It's not encumbered by patents and so on. I think I will get into this again, actually, so let's move on. Now, the whole bootstrapping issue that I talked about, a lot of it involves libraries and just boring, annoying things. Now, Quick Lisp and ASDF2 right now are real godsends already in that regard. General Purpose Declarative Language is our product. It's mainly based around this define object operator. It's a macro and define format, define length. So that's basically what the system is 3 macros, mainly the one. It's been referred to as resembling a frame. So what we have is called a dynamic. Of course, Lisp is already dynamic, but declarative, that's new. Object-oriented, it's object-oriented in a bit simpler way than full class is, embedded in Common Lisp. So it's a superset of Common Lisp. It allows any type of an engineer to define problems in what should be an intuitive way for them without getting into all intricacies of Lisp and the different styles of programming, everything that you can do. It also provides a server solution for web deployment, by the way. We are in this camp that says the UI is the web browser. So dynamic, you know what that means. The different thing here that GDL really adds is that the definitions have no begin or end. So there's no procedural flow in a GDL framework. But we have dependency tracking and caching. But most of this stuff you already know. It's already there in class. Clear separation between definition of an object and an instance. Sometimes it takes people a long time to get that. And of course, it's a learning tool on any number of levels. When you're working with GDL, you're learning about GDL. You're learning about your application domain by trying things and seeing how they react in real time, usually. So this is a table that lays out the difference. Now, this again is intended for the audience of people that will use GDL. They don't know about class object systems, or they might, but they don't have to. And the simple way that we explain this is that a function takes some arguments and it performs some side effects, possibly, and returns a value. And with an object, instead of arguments, it accepts what we call inputs. It can perform some side effects, maybe, and then it computes a set of outputs. So they really do the same thing. There's 2 different ways to use it. A function, you just call it by name. An object, first you make an instance, and then you have to send messages. So it's a message passing. It's emulating a message passing system using class, of course. And this is how you define it. So it's similar to a def fun form, but define object with a name, a mix-in list, like with class, and then all the specifications. And the specifications are really like filling out a form, and you'll see that. Because it's declarative, you don't have to think about procedural flow. And 2 ways to decompose complexity. You can have an object which inherits from other objects, normal object-oriented inheritance. You can also have an object include children, and that's like a has-a relationship, a containment relationship. So if something, your computation you're doing in one object gets to be too complicated, you shove it into a child, delegate it to a child object, let the child handle that complexity. So this is the basic syntax. Definition name, you don't need all this detail. These are for people who who are coming fresh into Lisp. So this is the basic syntax, mix in specification. Then the specification are these p-lists, sequence of p-lists, and they don't have too many sections. They have computed slots, input slots, and objects, which are child objects. And yeah, they also have functions. You can have functions that take arguments. So the computed slots are just like a let form, so a name and an expression. But there's this unusual use of the word the, and that is one symbol that we shadow from Common Lisp, and this is GDL's the, which is a reference macro to reference the value of this slot gamma, which is over here. And it does all the checking if the value is up to date, if the cache is up to date, or if it has to be recomputed. What this is really computing in this example is this value speed. It's not obvious that that's the output, but with some documentation string, you could see that that's the output. But because these are listed in alphabetical order, the one that's the output and the one that are the intermediate values could be intertwined. So give it name. So again, it's the message passing paradigm as opposed to the generic function paradigm that we see in CLOS all the time, where you don't really have objects, you just have this collection of methods that work on types. Well, you do have objects, but the objects don't collect their methods. So then to use this, we have a make object, similar to a make instance, but it does make an instance, it does a little bit of other stuff. And now you can use the object, which is just like the if you have self set to something. So the self is just, or the is just saying the object self. But the general case is you can say the object and then give any expression that returns an object and then a message or a reference chain to a message. And that's how you get your answer out. So input slots is the next one. That you pass the values in when you create the object. So when the object is made, it takes a keyword argument list of the input slots. And now you have your object, but it has not actually computed anything until you ask for something like the speed out of it. And you have another section of this P list called objects. Now objects is takes a list of lists, so it's similar to let in a way, and that's the name of the child object. But instead of just an expression, it takes another P list, because you have to give it a type. You do have to specify the type of a child object. This can be referring to a message, by the way. It doesn't have to be hard-coded as a symbol. It could be the so-and-so type, but you do have to pass it in. And then the inputs, the values that will match the input slots for that type. So now you see where we can start to build up a tree of instances, because if these definitions themselves also have children, now you end up with a tree at instantiation time. Now it's very common that you put child objects into a sequence, and this little bit of syntax for that is you say sequence. Now this colorizer isn't smart enough yet, but in the Emacs font lock mode, this color's in a different color, because there are a few of these keywords into children that have special purpose, like sequence. And this sequence is a size sequence, because you have different types of sequences. And then it takes a number. So this is essentially an array, or a generalized sequence. And this is one place where we've seen, GDL has its own sequence type. It's defined as an object. It has operators on it. And it would be really nice if we could just extend the common Lisp sequence type so that, obviously all the normal list operators or sequence operators would just work, and then we could add some of our own. Right now you have to say some elements or list elements. You have to do something to pull the sequence out into a normal Lisp list, which is a bit tedious. But that's there right now. We also have to learn how to use sequence package or iterate package or something, because we tend to do a lot of this map carring on map carring, which is not proper, but that's a separate topic. That's really an application issue, not so much a GDL issue itself. It's so easy to do these kind of things where you're generating 5 lists when you really don't have to be. So to refer to our syntax for referring to a sequence element is you just wrap it in extra parentheses. This is a reference chain, so I say the object, and then speeds is a sequence. So now I wrap it and give the index number, and then another message which is inside that object. So we get and functions are just like computed slots, but they're not cached, and they take arguments. So to call this, you would say the, and then open bracket speed and give a temperature. So you're trying to get the speed of sound at a particular temperature, but you don't want to have to make a new object just to specify a new temperature. You just can call the function with a different value. So that's the overview of the syntax. That's basically what there is to know about GDL syntax, in addition to the common Lisp that you use for the expressions, for the individual expressions to compute stuff. We can go a little bit through geometry, but I think what I'd like to do is, because this is it's more of the same stuff, it's just instead of a speed of sound object, you have a box object, or a B-spline surface, or a airfoil, those kind of things. Okay, so we define geometry the same way as any object, and GDL has built in some simple wireframe geometry objects like boxes and spheres, cones, and for more involved geometry like solid modeling, we have an interface to a solid modeling kernel, which is a commercial C++ library that we license the source code and distribute the library. So with base object, you get a basic coordinate system, length, width, height, and a center and an orientation. So those 5 things are enough to fix a reference box in space at a given orientation and size it to a certain scaling. And then we have functions, standard functions that work like anything else for all your normal vertex, face center, edge center, all these standard CAD type of operations. So you have a single box. This one just has hard-coded values for computed slots for height. And then it has the child is actually the box. Typically, the geometry will be at the leaf level of a tree structure that you would come up with. That's what I say here. And then, we have trickle-down slots. If you say something is trickled down, then you don't have to pass it in as an input. But as you can all imagine, that's pretty dangerous to do, because if you're working inside an instance and you see a value there and it's not declared as an input slot, you have no idea where it's coming from. It takes some detective work, but they can be convenient. So vector is basically an actual Lisp vector with 3 double float numbers in it. And we do, that's the basis of doing everything. So positioning things, you give it a center with a certain, transformation on the center that's coming in, and so on. So people are building up fairly sophisticated applications with this stuff. I think you'll see some of that a little later in some of the lightning talks. And finally, when you get it, the way that we look at human interfaces is it's the same paradigm again. So base AJAX sheet is the latest thing. It used to be base HTML sheet, but now it uses AJAX interaction. And you mix that in, and then you specify a body, and that's CL who. But you have the reference macros inside there. And then from there you go in with having separate slots for sections of the page. So those sections will update on demand, based on dependency tracking using the AJAX. And by the way, this is available on GitHub as of this morning. The GDL core system is licensed under AGPL.
Okay, good afternoon everyone. My name is Toby van den Berg. I work at Delft University as a PhD candidate. And we actually, at the Department of Aircraft Design, we are using GDL, which Dave Cooper presented earlier today, for aircraft design cases. Well, I'm going to show you an industrial test case for aircraft wiring manufacturing. So my objective is to show the use of Genworks GDL in this industrial case. And this industrial case is for a Dutch company called Fokker Elmo, and they produce wire harnesses of airplanes. Wire harnesses are the wirings, the cables that are in the airplane underneath your feet, making sure that you have power for your entertainment system, for the engines, for all the electrical equipment everywhere. Those cables go everywhere. Well, I'm working on this project with a couple of partners, the university obviously, the Dutch government, and Keyworks, a startup, actually also developing industrial applications in GDL. Well, aircraft wiring, this is a picture of a lady actually manufacturing these wire harnesses in China. So you can see that it's a very messy thing, very thick cables. And well, it comes with a couple of issues. It takes a lot of time, so that's one. Obviously, in terms of cost, a very big issue, and quality. In the aviation industry, quality is extremely important. So, how are these things developed? Very quick and dirty. They are designed in a 3D mock-up using traditional CAD packages, like CATIA, for example, and then a production drawing is made of them, which you could see on the previous, on this picture. You see the drawing underneath where the cables are laid on. And in the end, so you have to go from this 3D model to this manufacturing information and this drawing. So they do a couple of things. They analyze their 3D design, they transform it to a flat geometry, and they arrange the layout such that you can actually produce something. Well, this comes with some problems. First of all, there's a lot of geometric analysis in there and manipulation, which costs time, which is difficult. The work itself is very repetitive. It's all manual, well, clicking, a lot of it in these CAD systems. And well, another characteristic is that it's based on the knowledge of the expert, so of the engineer doing the actual work. And well, they're constrained by experimental data as well. So what do we want to do? We want to decrease the time it costs to generate these drawings, and we want to increase the quality. And we think that we can do this by automating these tasks of creating these drawings. So the method that we selected was actually to capture all this product and process knowledge in a so-called KB application. I'm not sure if Dave explained what the KB is. It stands for knowledge-based engineering, and it's more or less the merging of knowledge-based systems and parametric CAD. And we are doing this using a GDL, which is our KBE system. So the implementation, what does it look like? In GDL, the whole product model of a wiring harness is generated generically, so it consists of objects such as bundles, connectors, and well, you can see here in the picture that this wiring harness, this 3D wire harness, consists of these things. Well, each of these objects can be analyzed, has the potential of self-analysis, and well, can be transformed from for example, the 3D domain to the flat domain, and you can all access it via the web. Well, and just to show the application itself. This is an example. So the interface is also made in GDL. You see here the 3D model of the wiring harness, and well, just by simply clicking on a button, it will be flattened to a flat plane. And doing this in the correct way, including all the analysis, is done live here now. And the engineers really at the work floor take days to do this properly, with all the quality checks to make sure that your airplane does not drop out of the sky. Yes, it is still there. Okay. So just to show you, this is the same model, but now it's fully flat, and now we can actually start making the final production drawing from it, but not in this presentation. Thank you. This program? No, this program is not open source. It's developed with Fokker Elmo, the company. So actually, it uses their expert knowledge, so their advantage. And it's really built into the program. That's one of the things that GDL allows. You can really model geometry in a very convenient way, analyze it, and incorporate all this corporate knowledge into this application. So no, we cannot provide it. They will not let us.
All right, so that's loud. If I looked at the agenda well, I was the last speaker for this afternoon, so I feel honored. I also feel honored to stand to such a big crowd of very experienced professional programmers, which I am not. I'm an aerospace engineer. I'm currently pursuing a PhD in aerospace engineering at the University of Delft, similar to Toby. I was under the impression that I had 10 minutes to talk, and I just found out I had 5. So I hope on your patience to allow me for 5 extra minutes, and maybe also of the patience of the referee at the left-hand side. It's a lightning speech. I'm getting all energized right now. Dave told me, can you give a flavor of the flexibility of GDL as a language? I said, sure. So I want to concentrate on 3 things. GDL has different users, and all those users have different wishes. For example, the programmer sees the code, and he might say, I want a high-level language. I want good documentation, should be a sexy language. Maybe that's my own requirement. Then there is knowledge which enters GDL, like in the forms of rules, parametric rules, production rules, and they form the eventual program. That knowledge is typically residing off the head of an engineer. He holds all the knowledge in his head. He says, I don't understand code, I don't even want to understand the code. I want you to open up that black box, that application that you made, because I don't know what is going on under the hood. But let me enter new knowledge in case my design rules change. Now, then you have the interface, and typically at the interface, you might see a designer, which is looking at the design, as it is. And he has requirements, like, let me inspect different product aspects, give me a professional visualization, and let me interact with the geometry. And then finally, there is an idea in a design that you iterate over your product a couple of times, varying parameters, and try to optimize your design for a certain discipline. So you want to rerun, let's say, things a couple of times. So the researcher, the optimization expert might say, I want to explore the design space or optimize product parameters. So what you see happening here is a pool of GDL by different users. And for those different users, except the programmer, I want to give you a little bit of flavor of what we are researching currently. So first, the knowledge part. Important to understand is if you go to a KB application, that is a whole process. So at the left side, you start with raw knowledge. And in some way or another, you have to translate it into code. Well, that bridge indicates that is a process. That is not something which is extremely easy. To give you a flavor, this is an aircraft elevator model. And if I talk to an engineer, that engineer is going to explain me in a sort of informal representation of his knowledge, how that product is decomposed into components, parts, etc. That is an informal knowledge because we can all understand this. If we map this onto a formal layer, which is closer to computer code, I might want to represent this in more like a UML style way. Finally, this should become the code. This something that the programmer understands, but the engineer not. This process, going from informal knowledge representation to formal to KBE, is something that we're trying to smooth, to find a methodology for that. And here you see the informal, formal code. What we try to do is to implement this methodology called domain-specific modeling. So you create an environment where at the left side, the engineer, for example, can model his domain, his knowledge, then maps that onto something which is more formal, and then code. So from left to right, code generation, from right to left, round tripping. We have to map something, we have to translate something, and if something changes in the code, I want to map that back to the model. Now, to give you a flavor of how we did that, the top screens are just a user interface that we were developing, called it user client. And we started storing all that knowledge into Allegro Graph, which is a Allegro product. And based on, I also want to show a nice movie, if that's allowed. So what we did, we feed Allegro Graph with ontologies and rules, and with legacy data, maybe residing in different relational databases or other facts, and we provide the user templates based on ontologies to model his knowledge. Such a model represents the facts of the product, and they go back into Allegro Graph, which would allow Allegro Graph, or at least the code that we've written around it, to generate more formal representations to which another user can have access, and maybe other facts from it. Now the idea is that then finally we have a Lisp client, or GDL client, which queries Allegro Graph to retrieve the knowledge which is important, and would allow it to write code automatically. That auto-generation of code is currently something we're demonstrating. So this is flavor number 1. Then flavor number 2 is the interface. So you already saw an interface in previous presentation. Basically, GDL, you see in the middle, which is the code. Then at the left is the geometry kernel that is under the hood. So it's a library of functions. And at the right is the interface, of which Toby already gave an example. Now, we said if we look at current technologies, emerging technologies, there's something called WebGL, which is quite a nice technology. It's OpenGL in the web. Can we couple this to GDL? Well, we tried. In a couple of weeks, we were able to. So the idea is that in the user interface, there are Ajax queries. For example, I want to manipulate an object, display it, or I want to change the shape. Then GDL is starting to do some dependency tracking. How does this object depend on others? Does some calculations, does some calls to the geometry kernel. And then finally, geometry kernel gets back to tessellation, which is a triangulation of geometry. Then GDL updates, let's say, the interface, sends some JavaScript and stuff. And then finally, we see the result. I have a demo of that. That is showing. To explain the difference, in the initial stage of GDL, everything was 2D geometry, so it was PNGs, JPEGs, everything. Then we chose VRML, but it had some limitations, so now we have a coupling, I think, to WebGL. So what you're seeing here is a product tree on the very left with a robot army, so there are 100 robots, and the user is visualizing such a robot, rotating it, and this is all in the browser. And he can select things and inspect their properties, but he can also change some properties of objects. So in this case, we're going to make the left arm of the robot a little bit thicker, and that you saw, it was happening real time inside the browser. For example, change some colors. Of the base in this case, I want to color it red. Basically, the idea is that you can really manipulate your geometry inside the geometry. Now, in this case, we were showing all the 100 robots in here. The performance is reasonable, I think. It's pretty fast. We support different types of rendering. And I think you got the main message, and you can skip the rest of this movie. Yeah. Then the final slides. The final thing was, if you want to optimize, what you basically do is GDL contains the product. It contains the product knowledge, a definition or a model. Then the code to run aerodynamic analysis or structural analysis are usually different tools, different simulation tools. And what you can see is that GDL is a lot of times being just an application inside a big simulation workflow. Now, such simulation workflows, stuff that we're using in Delft, and these simulation workflows have software that automates, let's say, a simulation process by automatically executing applications, by reading in inputs, outputs, etc., taking care of the exchange of information. And part of such a workflow is everything that GDL should do. And what we have developed, let's say, is a good way to form communication between the optimization code, for the automation code, and GDL. And we use the HTTP REST query protocol this way, and then GDL is sending back the results. Yeah, I think that was it. If there are any questions, I would be happy to answer those.